Hello, welcome back. Moving on, part two, hopefully the last bit on this relocation stuff, which has an important point that I'm trying to get to. But let me first tell you about the rest of my little story. What happened was, typically, when I discovered a new trick. And my new trick was based on this. See this file we've been working with? This dbg dump. I added, it's 2 bytes bigger now. I added the jump at the beginning. So as you can see, that's essentially the same thing we've been copying all over the place. It's easy for me to find out the size of the file just by inspection, and so that allows me to do this. I could say this. Well, I'll go back in there. It was 2. The end is at 2A3. Okay. Now, aside from this bit, if I put a bunch of dBs in front of here and some semicolons along here, then what I have is code that I can put in my ASM files. Oh, and get rid of the dashes. So in a few steps, I can turn this into code that I can put into my .asm files, and it'll compile. I can put a label in front of this, DOS debug dump, and give it an address, and compile it into my other projects if I like, rather than going through that complicated mechanism of what we did before. So I wrote a batch file to automate the whole process, or at least part of the process. And as usual, once you start on something like that, it's kind of hard to stop. And I have to go back to broken. So I started on this group of functions. Now these little ones here are used by the debug dumper thing. I don't know if I did them, but I started just going through them one at a time. The little ones, not this. And I thought, oh, I'm gonna make a dump file for everything, and then whenever I need them, I can always, bring them into my files. Everything was going along great until I hit this one, put S. And then I realized, well, put S relies on, or calls, strlen. And then I realized, strcar also calls strlen. And then strlen also needs an address related to strlen, and so on and so forth. So then I thought, okay, maybe I'd better make a function at least for setting that terminating character, because for instance, strlen sets it directly. I showed you the code, I think. Well, I showed you it in this. This is a different function, but I think strlen does the same thing. It examines this address in memory and copies the byte to or from this address. And this address is would be in the table of defines when you compile a program, but it's definitely something that you can't pre-compile. The dump things are things I wanted to not have to modify. So let me show you my directory anyway. See, I started doing these dumps, and I stopped at put at. In fact, I can delete this one now if I want. I decided, okay, well, all those things depend on each other. So what I'll do is I'll do just like for this guy. Here's the dump, the memory dump of that file, of that binary. Put all the functions, those functions that are related to strings in one file, and then I only need to compile it once because everything's relative offsets, even the terminating character, right? Wrong. That's the problem. The problem is that terminating character. See here, I've got a nice list of all the offsets for each function. I think that last one is 94 plus 1. And of course the address of the terminating character is here. However, if I go ahead and move this code inside the binary or in the compile process at some point, and this position changes, then everything else has to be recompiled. It might depend on that. But that might not be so bad. For instance, we could put that in a global table, and then everyone can access it that way. And that's one solution. A way of using indirection and letting it have a fixed index in some table or something. But I wasn't happy with that. I wanted it to be more like the dumping thing. I didn't want it to have to depend on that. And in a sense, I think of this byte as more of a property of this group of functions than as something independent. It sort of belongs together with this. You can think of this set of functions as all belonging to a certain class. They all belong in a certain category, and you can think of this whole thing as defining a type of category of operations. And this is just simply a property of that category that belongs with it. And it doesn't really seem to make sense that not only do other modules and functions require recompile if this thing moves, but you have to recompile this thing. It doesn't work. That was the problem. I was hoping that maybe there was some way to get a move that was use a relative address, but there doesn't seem to be anything like that. Go back to broken. Oops. See, the great thing about those jumps and calls is that it's relative addresses. But there's no, as far as I can tell, and I might be wrong, and I'd love to be shown wrong. There's no relative move. Suppose I make a temp directory. Oops. Okay. I compile this thing. I set strlen equal to 100. Alright. Now, I want to compare that with a jump. It doesn't have any jumps. Let's get another one. That has jumps. What calls? Put s. I'll make this 100. strlen we don't know about, but assuming we put them all together. Okay, let's put strlen in here at 200. And I can inject that in later. Let's try to make the file big. End of file. Thousand. This is just a trick to get it to be bigger than the thing to be bigger than just a few bytes. Okay, we got a nice big file. Now, if I want to put according to the ASM file, strlen goes at 200. So I now have another batch file, inject. But in order for it to work, I have to make sure that I put this strlen here at the address specified that I want it to end up in the other object file. And so this has to give 200. So plus 100 minus 2. Do that to everything else. And that should do it. And I want to put that into puts obj. Alright. Okay. Now you'll see that this is simply the number I defined it to be. The address of strlen minus 1. What I really want it to do is not have that address in the move instruction. I want it to have a relative address. For instance, like puts has. Here's puts. This call 200. There's no 200 here. All it is a difference. You know, the difference between the return address and where the call is issued. And as far as I can tell, and everything I've tried, there's no move or compare or anything that uses a relative address. These jumps are all relative addresses. You know, everything else. Actually, this. Oh yeah, okay. Code-wise, things are movable, but address-wise, things that you use the move command with, those things don't move. They have to be compiled into the program. And that's why people make tables of addresses in order so you don't have to recompile everything all the time. There'll be a fixed address where say that byte is or a function might be, and so you get the address of something from a fixed, never changing address, so that when that address moves, then you don't have to change your code. It's just like that job file table in DOS, if you recall the second level of indirection for the files, the file handles. One thing I thought might work because of this thing, I can safely assemble a 140. One thing I noticed was this. In some other function, I had something like this. Not this function. I'll pretend this is a different function. It pushes a value and calls something else. Let's say 140, 150. Okay? The typical caller cleanup call. Now the usual thing here for the enter of code is push BP, move BP SP. We know that already. And in fact, it was that debug dump thing that I noticed this, and I subtract from SP 100, and that's an allocation of 100 bytes off the stack. Okay. Now, what I wanted to do now was load into the destination index the pointer on the stack to copy the data that I had planned to dump. So I would do something like move into DI, and then I said, okay, well, the address, I know where that address is. It's at BP minus 100. That's the beginning of the array. And then I would start to rep and move and so on. Now I'm gonna execute this code and show you what happens. Now it doesn't matter what these values are. Push BP, move BPSP, that's normal. Subtract from the stack pointer. Now, the stack pointer is at FE8. Okay. In order to get the address of the data, where the data would be stored, right? That address is 100. The beginning of that address, or the end of that address is at 100 SP plus 100. So this should return FE something anyway. Okay. But watch what happens. Look. Watch what happens. Move into DI. Oh, oops, that's not what I wanted to do. I didn't want brackets there. Hang on. 157. No. move into di I bp minus 100. Because if I take away 100 from bp, I should get FEE8, and that's what I want. But look what look what it puts instead. Now, that's not what I want. That's not the right value. But I noticed this though. There's another instruction I remember about called load effective address. And the way that one works is it sort of takes care of, it sort of removes brackets address wise. Like if I say BP minus 100, if I just said BP minus 100, I'm not sure what it'll give me. But in this case, it takes this as a pointer and then returns me the value of the pointer value for this expression. Watch what happens when I execute it. So load effective address into di of BP. See what it's done? It's like the reverse of what this thing did. And now di says FEE8. So exactly where the stack pointer is. So I thought, maybe there's something going on with this LEA. Maybe that might work. Remember, where did I put string length? 200. I thought trying to use a LEA instead. Like find the address of, return me the effective address of my position minus 1 or something, and maybe the binary code would not have a hard-coded address in it. It might be something relative, but it's not. It doesn't work. Okay. But I did actually come up with a solution for this problem. And if you're ready for some wacky little coding, then I'm going to tell you about it right now. I'm going to take a little break for myself, and I'll be right back. Okay, was a much needed little break. Now this is sort of where we were examining that debug dump thing. Now, going back here, here's that string.asm with the fix that I came up with. Now, in fact, this is not something that's used in any code anymore. You wouldn't be able to do this today because this is writing to directly into the code. Nowadays, everything is protected mode, and you can't overwrite code. The data is separated from the code. But in those days, you could, in the 1980s, you could do this sort of thing. And so I'll show you what it is. And it's a very good analogy for what I'd call a C++ class and its associated data. String here we can think of as a collection of operations. Okay, so like a category or a class, and it has string lem, string and lem, the one we invented, put s, and now this set the string terminator thing, which I'll get to in a minute, and a function for retrieving it. So you can set it, or you can retrieve it, or you can do both at once. So it just exports the underscored things, and these are related. So here's the idea. I moved it away from stringlen -1. Turn it into a function to get and set its particular value. And as before, it's still in the code, but I just didn't want to put it in front of stringlen in particular. I thought it would be better off going together with the get and set. This set of functions. Well, that's not a function. That's just a label. And here's how it works. The set function was the one I did first, and it sets the value and returns the previous value so you can restore it later. Now the get one just calls the set one with a flag. I decided to use the high byte of the AX register as a flag. So in the help file, it might say, sets or gets without setting, based on a high. Or, if the value is less than 100, then it sets and returns. In any case, here is a regular call to what I've called trick stern. Now, the reason this has this name was because all these had similar names, and that it was getting so mixed up with the search replace that I just gave up trying to add more and more underscores and gave it a different name. For me, they have to be listed in order that they appear in the code, or else I just can't read it. I get lost. Alright, so what's going on here? Someone calls this set string terminator, which comes in here, and they pass in on the stack basically a character value. But as an int, like to a register like AX, you can't push a value smaller than a register, I don't think. Maybe you can. And now it calls into this little trick function, which again has its own stack frame, and it's going to use SI for something or other. So it saves that off. And now, if you recall from many lessons ago, BP-2 contains the return address of the function that called this function, which is this function. And at the return address, here, I've put in the binary code for a jump to IP plus 3. It says here, jump to IP plus 3. Or if I wanted to add more data bytes, I could increase this number to, if I wanted 2 bytes, I would make it a 2. All the way up to 80, I think, is the maximum. For a conditional jump. It doesn't say, oh no, it's just a short jump. No condition. Okay? That's what EB is. Now, following the jump here is the actual data. I wanted to be sure it was something I would recognize. I could change this to something else. 56 or something. Maybe that's easier to recognize. This is the terminator character. That's EF56. The default would be 0 normally. So normally there would be a 0 here, but for my testing I wanted to put something I would recognize. And so this calls this. He retrieves the address of his return address. So that's this, the pointer to this EB. Add to, okay, and that gives you a pointer value pointing to this address. And SI, sorry, SI would be pointing at this address. If I add 2 to SI, right, then that gives me the address of this, and I can move that into my A low, 0 off the A high bit, and again I've got one of these funny jumps. Oh, that's another 0 off. This is checking whether or not to set. It's something I added in later. I just wanted to get without set function, and so I'm getting so used to these these little jumps that I'm starting to learn them by heart. 74 is jump if 0. 75 is jump not 0. A value of 0 in here just jumps by 2. It jumps to the next instruction. And so, 1, 3, and so on. So I'm saying if the comparison resulted in 0, then jump over this jump, because this is a 2-byte instruction, so we've got to jump to IP plus 4 to execute the setting code. Otherwise, just go to leave. And that actually works. And I can demonstrate it working quite easily by just compiling this and running it. Maybe I'll copy it into our temp. I gave addresses. But how am I going to call something? I better make a test program. I have a test program, okay. Let's put string len at 200, and that would mean, well, we'll find out in a second what that would mean. I'm going to set that in here. Luckily, you can do simple arithmetic. Oops. To make 200, I just have to add 100 to this, and the rest. And then I already compiled this, I think. Yeah. Oh, I want to inject. Okay, so now we can read off some of those addresses. So get is 290, and we lost it. Okay. Get was 290, and set I have a way of doing this quickly, but tell me some steps. Alright. Set S term, where are you? Here. 271. So we can take these defines, the ones we need, and put them in our program. Not very well lined up, but it'll still work. That doesn't work too bad. These are internal. This is internal. Internal. There. Okay. So let's just see if we can retrieve the value. So that requires no arguments. Get string terminator, and it should return its value in AX. Okay. Any problem? No. Okay, let's see if it works. Well, that's the debug dump. Oh dear. Oh, well, there it is. Okay, 56. Now, here's the thing. I should be able to move that code anywhere I want, and I'll still get 56, and I'll still be able to recall and set it. Because you'll note that I always do that. There's nothing in the code there that referenced any particular address. But I want to trace through it anyway. Trace. Okay. Oh. That would have been, yeah. That was the function. That's not that. Oh, I took away the, okay, that's why. I replaced what was there before. I was expecting. Let's just make it easy on myself. Okay. All right. Now we're just calling it. Now this is the just the get. So the way that the get works is that puts a flag in the high register, mini register, and now it's calling the first step, the function that calls the second function that uses this return address in order to retrieve the byte following the return address. Okay, sets up his own stack frame. That might not be necessary, but now pushing the value that was passed in to him, I passed in 100, call, set up stack frame. Now move into SIB. This is the return address. So SI is 278. Okay. That's an B. That's the return address. But that's what we expected. If I dump 3 of those, A, B, C. This is the value we're after. What happened? Oh, I already did it. This is a move. It added 2 to SI, 1, 2, retrieve the value 56. And now it's just checking whether or not it's supposed to store the passed in value as a new value. And we got a non-zero answer, so we're not going there. We're jumping to 299, which is the way out. And now we're going to land on another jump. This is that one again, the one that I just coded in binary, which jumps over our byte that has now been read. Store the stack frame, return from there, store stack frame, restore AX, return, return. And we got 56. Now, that code is not very big, obviously. And where does it start from? 200? Where do we put it? 200, yeah. It's not very big. Where does it end? Oh. Oh, I know how to find it. Did I actually compile it? I've got string.obj. Just want to see the size. AB, so it's less than 100. Not here. So it's currently at 200. What I want to do is relocate it. And I'm going to use the same trick as before. I'm going to fill stuff with CCs. How big is my program? Not very big. Test OBJ. No, test OBJ is big. Oh, yeah, mine is big. Okay, let's fill from 300 to CCs. We used to have DOS debug dump in here, but now I'm going to obliterate it. Okay. Now here's the function that we're going to move, and it's at 200, and we said the size was AB, I think. So let's say 300. We're on the safe side. I'm going to put that at 1, 2, 3, 4. Okay. And should be covered in CCs. How many? Too many do I have? There's going to be some junk in here. This looks like the last function. 200 to 300. Oh, okay. Well, I'm not sure exactly why, but I guess it looks like I have. It looks like I got all of it. 1, 2, 3, 4 plus the size of. Well, let's hope we did. Go back to 100. Now, there's just a call there. And I'm going to fill up this stuff with CCs. To 300. Okay. Now we got nothing but C's. I'll write it out. So now the first thing is stirlen, which is at 1, 2, 3, 4. So we've got to figure out where we're at, where we're calling. But that's not so hard to figure out. We went from 200 to 300 to 1, 2, 3, 4. If I add that and subtract 200 to everything, then that should give the right answer. Okay. 1, 2, D2 it says. Certainly. So far so good. There's our 56. There's our not setting. There's that jump. Everything relative addresses. And we're back to where we started. And it worked. So now we have a way of binding code and data together. And in a sense, this whole thing is leading to the idea of binding code and data, which is one of the principles of C++, which is looking for a way, a language, in which the separation of code and data is obscured somewhat. There's less of a differentiation between code and data. Certainly some types of code have data associated with it, and a language that is useful should make it easy for programmers to associate code and data and bind them together like we've done here in this particular case. Bound that code to the data that it relies on in such a way that this whole package of string functions is now just a unit that I can move and put anywhere, and it will continue to work as normal. Okay. well, now that that's done, I can fix up the rest of the project and do what I, what I had to do. The reason I actually went this far was because I have to actually move those functions, and I didn't want to go and have to recompile everything else that depended on them. So, okay. Next will be another walk on the wild side, even crazier than this one. So be prepared. Bye.